Is my screen visible?
Yes, yes, it is coming up.
So, welcome to week 5 content. So, in this week, the topic that we will be discussing is on evolution. Okay. So, the question that we are discussing is more is about our ancestry, like how we evolved. There are many species in this world, and we just want to see how we are connected or not connected. So, if you take the DNA sequences of two species and you start comparing these DNA sequences, you'll notice that several portions of this DNA sequence, about 90% or something, of these DNA sequences are same with respect to these are interrelated species, like but most of the species you can go and look into that. There are researches which prove that these DNA sequences for about 90% of the DNA sequences are similar in multiple species. So if you so there must be some kind of a common ancestor from which we have evolved. We have slowly mutated and we have evolved into different species, right? So this is what we will be discussing for this week five in this week five. So we want to find our ancestry, and more specifically, given our multiple species, we want to construct this hierarchical tree or the evolutionary tree. So, for example, what coming to this point of evolutionary tree, what evolutionary trees are is like suppose these are like family hierarchy kind of a thing. Like suppose in the family hierarchy we have our grandparents, and from them we have our parents, we have a mother, we have a father, and sorry, there are different parents from mother and father. So we have a maternal grandparents from whom our mother is the child of our maternal grandparents, and we have paternal grandparents, and our father is the child of our paternal grandparents, and then we are the children of of our parents, right? And then there is our brother, then sister, then ourselves, right? And then we have our uncles and aunts over here from this kind of a tree-like structure. This is a tree, if you can notice this, right? So this kind of a tree-like structure is called as a evolutionary tree or a family hierarchy. It's more specifically this is called a family hierarchy because it is concerned to one particular family. But if you come into multiple different species of different species like a cat or a mouse or a rat or a monkey, if you take these multiple species and you construct their family hierarchy, like how they have evolved from their ancestors, that is called as an evolutionary tree. Okay, so this is basically a hierarchical organization of these different species. And how it will look something like this: there is some ancestor, and from there we have evolved into some two species. Then there is some other ancestor. From here we have monkeys and chimpanzees and something like that. Interestingly, we don't know these ancestors, so these are just nodes without any name, right? But we'll see in due course of this discussion that the age is like around how many years ago this ancestor existed or this ancestor evolved into these two different species. That we will be able to know, but we don't really know how this ancestor looked like, how it's how what was this DNA sequence, how they look like, how what was their name, and anything about relevant this kind of an information about these ancestors is still not known. So this is what about the evolutionary trees and how we find the biological question that we will be discussing is about construction of this kind of evolutionary tree. Okay, so for this construction, what we need is what is called as a distance matrix. So this distance matrix is something like we have this distance matrix. It's basically it looks like this matrix format where we have all the species, and we want, like, let's say this is species A, B, C, D, and E, and then we have again A, B, C, D, E, and this is basically this matrix. Every element of this matrix stores the distance, how far. It's a measure of how far the DNA sequences of A is from the DNA sequence of B. How similar is basically which of the how many nucleotides are same, but the difference distance is basically the opposite of that. How many nucleotides are different? So from that we can say that this gives us a distance matrix is basically how different. This is a measure of how different these two species are from each other. Okay, so we keep that in each of the rows and in each of these in this distance matrix, we store that information. So obviously the diagonal values will be zero because A and A are the same species, so their DNA sequences will be same. So we will have the value zero for the diagonal values, and then for each of the this will be a symmetric matrix as you can see because A to B whatever is the distance and B to A will be the same distance. But if you consider this DNA sequences as like strings, then you will notice that this distance between A to B is basically the Hamming distance between these two strings. Okay, so that's all about this distance matrix. Yeah, there is something called as an additive distance matrix. What this additive distance matrix is basically if you have so given any kind of a distance matrix, I'll just fill it up something like 3, 2, 1, 1, 3, 4, 0. Let's say this is 1. So, this is 2, 3, okay. So let's say this is some kind of a distance matrix. Now, I don't know whether there will be some kind of an evolutionary tree between these species or not, right? So, let's say we are taking some kind of a subset of species. They may not be related with each other at all. So, it is not necessary that given a distance matrix, you can construct a evolutionary tree. These evolutionary trees are also called as phylogeny in biology. Okay, Phylogeny. They are also called phylogeny. Okay, so it is not necessary that given a particular distance matrix you can construct a phylogeny. Okay, so but there are some distance matrix for which there will be at least one phylogeny. Okay, such kind of distance matrices are called as additive distance matrix. There is a 4-point condition which mathematically can check whether something called as 4-point condition, okay, which can mathematically check whether a distance matrix has a phylogeny or not. But that is an extra topic which, if you are interested, you can read from the book. This there in the last extra courses, extra subsections on the of portion of the book. Okay, so this is called as a 4-point condition. You can look into that. Okay. So in summary, if it is an additive distance matrix, then there will be at least one phylogeny for one evolutionary tree that can be constructed on this set of species. But otherwise, we cannot ensure whether there is an additive matrix, whether there is a phylogeny or not. Okay. So the computational problem here is we are given a distance matrix. We are given this distance matrix and we want to construct the evolutionary tree for this set of species only. And we are going to make it a little bit simpler. Instead of constructing this hierarchical organization, we are just going to construct an unrooted simple tree. So initially we will look for algorithms to construct this unrooted simple tree. And then we will be looking into this ultrametric trees, which will be looking something like this kind of an evolutionary tree structure. This kind of trees, sorry, for which the age of these ancestor nodes are also known. This kind of trees are called as ultrametric trees. Okay, ultrametric trace, and we will look into an algorithm to construct this kind of a trace. But before that, we will look into two different algorithms for construction of the unrooted simple trees. Okay, so what simple trees are? These are unrooted trees, so there is no specific node called as a root node. But what happens is these trees are just unrooted trees, and simple tree is it's called a simple tree because there are no node of degree 2. So, like for example, consider this scenario. Suppose this is a tree. This is a tree, right? But this is an unrooted tree. There is no spatial node called as a root. So in this node, let's say this is a species A. This is a species B. This is a species C. This is a species D. Okay, and the distance these are the this is the weights of these edges. Okay, so these weights of these edges kind of denote how many years ago there is an evolution or there is this mutation from which this uh, creating some kind of an ancestor so that this species has evolved, has been formed. Okay, so let's say these are the weights of these edges. This is 1 and this is 3. Okay, so now notice that this ancestor, obviously there is some kind of a mutation such that this particular ancestor has evolved into this ancestor, and then this ancestor has evolved into this current species, which is B species. But we don't need, for the simple tree, we really don't need to find which kind of an ancestor this is or what this ancestor is. All we want to know is that how these species are connected, right? So we really don't want to know whether there was some kind of a species which look like white or black or like a monkey or like an ant. All we want to know is whether B is connected to A or not, and if they are connected, who is the common ancestor. So the common ancestor is this one. We don't really need this particular ancestor. So what we are going to do is we'll just compress these two edges into one edge, and we will form something like this. This is G, this is C, 3, 4, 5, 2, this is A. And this will be B, and the weight of this edge will, obviously you can just add these two weights, which is equal to 1 plus 3, and it will be equal to 4. Okay. So what it means is A and B have a common ancestor, and this ancestor evolved, mutated into two different species. One species slowly evolved over a due course of time, let's say 2 million times or 2 million years or something. After 2 million years, the first mutation, whatever the first mutation was, that had changed and slowly changed into to form this species A. And then the other mutation, the other kind of mutation that it had happened, that slowly mutated, and took 4 million years to evolve into this species B. This is what it means. So a simple tree is coming to computational aspect, like computer science aspect. If you are having this kind of a tree structure and there are no nodes of this with degree 2, so you cannot further compress it, right? You can have nodes with degree 0, you can have nodes with degree 1, you can have nodes with 3, 4, 5, whatever. But there will be no nodes of degree 2. If that kind of a scenario arises, then you can just, if there are nodes of degree 2, then you can just compress these two edges into one single edge, okay, to form this particular tree. So if there are no nodes of degree 2, then that kind of a tree is called as a simple tree. And we will look into two different algorithms to construct simple tree first, and then we will go into a construction of ultrametric trees, or whatever is called the evolutionary trees. Okay. So yeah, there's this theorem. You can look for the proof of the theorem in the book. This theorem states that if we are having an additive matrix, additive distance matrix, then there will be definitely exactly one tree will be there to fit it. Okay, one simple tree must be there to fit it. Okay, there is a unique simple tree to fit a additive distance matrix. So now we are looking to summarize, we are looking into phylogeny construction problem, and we have this distance-based phylogeny problems, which is basically we are given this distance matrix and we want to construct the phylogeny. There is this character-based phylogeny methods, which is basically we will look little bit later into this particular problem. And for the distance-based phylogeny, we will look into additive phylogeny algorithm first, then neighbor joining algorithm second, and then finally we will look into ultrametric tree algorithm. This is basically where we will look into the evolutionary trees construction or the ultrametric trees construction. Okay, and then there is this character-based phylogeny algorithm, character-based phylogeny problem, which we will look into very briefly into what is small parsimonies and what large parsimonies is. There are these two different variants for this character-based phylogeny. Okay. So to begin with, let's go to additive phylogeny algorithm. So suppose this is the distance matrix that is provided to us. This is T. Okay, so this is the distance matrix, and we want to construct the. So we have these four different spaces I, J, K, L, and this is the distances between I, J, and K and L. So we want to construct the simple tree that satisfies this additive distance matrix, and we will be using what is called as an additive phylogeny algorithm. So what we will do is we'll take the limb length, we'll let's say we will pick any spaces, at random. Okay, let's say we are picking J at random. Okay, we will pick one species at random. Let's say we are just picking J. Okay, so now we will calculate what is called as the limb length of J. So how do we calculate? This is the formula to calculate limb length of J. I'll show you an example on how to calculate the limb length of J. So for J, what we will do is we'll ignore J and we will take every pair of other species. Let's say we'll start with IK. There is IK, then there is IL, and then there is KL, right? So there is KL. So what we will do is we will calculate this, we'll apply this formula for each of these three pairs. Okay. So first of all, IK. Let's say we take IK. So what is the distance between J? We are calculating limb length of X, then we will calculate distance between D to X plus D X to Z and minus Y to X. Okay. So we want to calculate the limb length of J. So we'll take the limb length of J to I, which is 13. I'm calculating for IK. Okay. So this is 13. Then J to K, which is 12, minus I to K, which is 21. Okay. Divided by 2. So this value will be, this is 6 minus 1 is 5. 3 plus 2 is 5 minus 1. This is 4. 4, 2 minus 2 is 4 by 2, which is equal to 2. Okay. So for IK, the value is 2. Okay. Similarly, for IL, what is the value for IL? So I will take J to I, which is 13, plus J to L, which is 13, 26, minus I to L is 22. Okay. So this by 2. This gives us 26 minus 22 is equal to 4 by 2, again 2. Okay. Then for KL, what we'll do is we take K to J, J to the first character, which is J to K, which is 12, plus J to the second character, which is L. J to L is 13, 25. Okay. Minus K to L. K to L is 13 by 2. So this will give us uh, 12 by 2, which is 6, right? Is the calculation correct? Yeah. Okay, so this is giving me 6. So now, out of these three values, what is the minimum value? One is 2, 2, and 6. So the minimum value is 2. So the limb length for J will be equal to 2. Okay, so we take the limb length of J and we calculate the limb length of J, which is 2. And then what we do is we will calculate a variant of a distance matrix, which is called as D bar. And here what it does is, for this particular value, for the row and column of J, this row and this row, sorry, this row and that column. Okay, so for the row and column of J, we'll subtract by the limb length of J. Okay, which gives us, this is, you can notice here, yeah, all of these values are same. This is 21, 22. Then here we have 21, 0, 13, 22, 13, 0. But for this row and this row and this column, we are subtracting by the limb length of J, which is equal to 2. So 13 minus 2 is giving me 11, 12 minus 2 is 10, and 13 minus 2 is 11. Okay, so we calculate D board. And then what we do is we calculate the trim, wherein we just trim this row and this column. Sorry, this row and this column. We just remove this row and this column, and whatever is remaining is just written over here. That is what is our D trim. And we keep on repeating that. Now we perform it again, and this time we are taking L. Okay. So here we calculate the limb length of L. I will not be doing that once again. So you can calculate the limb length of L, and it is coming to 7. So I'll subtract the values for L by the value 7. Okay. So 22 minus 7 is giving me 15, 13 minus 7, 6, and so on. So then finally, for this is the D ball in the second iteration. And this is the D trim for the second iteration. So after that, we just remove this row and this column. Okay. So this is what we get. We now have just two elements, which is I and K, and two spaces I and K, and the distance between them is basically this 21 value. So what we will do is we will add an edge between I and K. So now we will go with the construction process. Okay, construction of the tree process. So we have this I and K, so we'll just add the edge between I and K. So now what happens? we have to add L. Okay, so now L can go back. L has to split these two edges only because it is a tree, so it is must be connected. So the ancestor to which this L is connected. So let's say my L is over here. So now the edge connecting L to this particular set cannot come over here. All the species and all the leaves of the tree represent the current species. So now I cannot make K as my uh, ancestor. Okay, so K is the current species. I can put in an edge with a weight 0. That will be a different matter, but that will happen, that can happen, that will happen, but that is a whole different matter. Okay, but the thing is we are adding L as an L is having some kind of an ancestor, so we must be an ancestor from which L has split. Okay, so that is what this, there will be some edge connecting L to this tree. So this edge must be splitting this particular edge. The edge connecting L to this tree must be splitting the edge between I and K. Okay, so that is what is represented here. There will be some distance from here to here, and there will be some values along this and along this, right? So if I'm putting an edge over here, what are the new edge weights? So L to K, what was the edge weight between L to K? Here we can see from D trim of the previous section, L to K, the distance was uh, L to K, the distance was 13, right? So if I don't know this value, if I don't know this length can be computed from the limb length. This is basically what is called as the limb length. So the edge connecting the particular species to the tree. Okay, so that is called as the length of. So the length of this particular edge is called as the limb length. So here I know the limb length for L is 7. So that means this is 7. I know the distance from L to K is 13 from this region. Okay. So if this length is 7, so this length must be 6. Okay. So 6 plus 7 will give us 13. Okay. So this is 7 and this will be 6. So if this length is 6, we can calculate this length also. This total length was 21. Out of this length is 6. So this must be 15. There is another way to calculate also. L to I distance was 22. So if this length is 7, so 22 minus 7 will give you 15. Okay. So anyway, so this is the tree that we got right now. Now we have to add J. So if you want to add J, you can notice you can either add J over here, you can add J over here, you can add J over here. So there are three different edges to break. So now we have to decide which edge to break. Okay. So notice that J to K distance, the distance from J to K is equal to 12, which is greater than 6. Similarly, the distance from J to L is 13, which is greater than 7. But the distance from J to I is 13, which is less than 15. So we will be breaking this particular edge. Okay. So we break this particular edge and we connect the J to this particular edge. And now what will be the distance of this? This is the limb length of J is 2. So the length of this particular edge will be 2. And now if this length is 2, I know the distance from J to I is equal to 13. So this length must be 30, 30 sorry, 11.
11.
Yeah, 11 plus 2 will give me 13. Okay, so now if this length is 11, we know that this particular edge was weight 15. This length was 11 now, so this edge has to be 4. Okay, so from this particular ancestor to this ancestor, I wrote it here, so it's basically clear here, over here. Okay, so this length was initially 15. Now this length is 11 because the limb length for J is 2. So if this is 2, that means this will be 11 because the distance to I is 13. And this total length was 15. So if this is 11, this to this must be 4. Okay. So this is the additive phylogeny algorithm. Okay. Next, going to the neighbor joining algorithm. Let's say this is it's the same distance matrix as before. So what it does is we will calculate the total distance. Total distance is basically what is the distance of that particular species to every other species. Okay, sum of that. So it's basically computationally speaking, it is basically the summation of every row. Okay, 13 plus 21 plus 22, 56. 13 plus 12 plus 13, 38. Okay, so it is basically the sum of the, sorry, sum of every row. Okay, so total distance of I is equal to 56, total distance of j is 38, and so on. Right. So now we will calculate what is called as a D star matrix. What this D star matrix is, it uses this particular formula to calculate the D star. So we'll calculate for a couple of values. So let's say we calculate the D star for I to J. Okay, this particular value we want to calculate. So we this is a symmetric matrix. This is also a symmetric matrix. So we just have to calculate on one side. Either we calculate the upper triangular and then transpose it, or we just calculate the lower triangle and transpose it. So because it's symmetric. So I'll just calculate for I to j. So if we are calculating from I to j, now notice that there are four spaces here. So n is equal to 4. Okay. So 4 minus 2 will be 2. 2 times distance to I to j, which is 13, minus the total distance of I, which is 56, minus the total distance of j, which is 38. Okay, so this formula, this value will be equal to minus 68, which is coming over here. Okay, and similarly we'll repeat the same thing again for this particular value j to k. We have the total. Let's say I'll calculate for j to l. Okay, for j to l. So the total n is equal to 4. It's still 4 species. So we will be having 2 times the distance from j to l is equal to 13, minus total distance for j is 38, and total distance for L is 48. Okay. So this value, if you calculate, this will come to minus 60, which is coming over here. Okay. So that way you can calculate all the values for D star, and that will give and then just calculate for one half of the one side, one triangle, and then you can just transpose it and put it into the lower triangle. So that will give us the D star. So once that is done, we will find what is the minimum value in this entire matrix. There may be scenarios where the minimum, there will be multiple elements with the minimum value, that this may be minus 68 also. At that case, this can also be minimum value. At that point, we will have to choose one of the elements at random. But in this particular scenario, we have this minus 68 is the minimum value. So we are going to go with minus 68. Sorry, here also we are having minus 68 between K and L. So there are two different occurrences of minus 68. So we can either choose I to J, or we can choose K to L. That depends upon us. Okay, this will be completely random, but it will be fine. We will get the same tree. Okay. Uh, Sorry, you may not get the same tree if this is not an additive matrix, but if it is an additive matrix, then you will get the same tree. So it doesn't really matter. So we take Ij, let's say for this particular case, we take Ij, and what we'll do is we'll just remove these two rows and two columns. So basically we take Ij and we merge it. We take this I and j species, and now I and j must have evolved from some ancestor, right? Let's say that ancestor's name is n, and is the I and j, m is the ancestor, common ancestor of I and j. Okay, so what we will do is we'll take this m ancestor and we will find the distance of the remaining species, which is k and l, to n. Okay, so to calculate, that is what is being done here. So we have m, and then we have k and l. I and j we have merged, and we are just going to its ancestor. Okay, we are taking I and j and we are going to its ancestor. Now we take this ancestor and the remaining set of species and compute the distance matrix. So how do we compute this distance matrix? For k and l, we are sure. We know that, right? K to k is 0, k to l is 13. From here, k to k is 0, k to l is 13, L to K is 13, and L to L is 0. This part is fixed. We can just copy paste from the distance matrix. But we don't know the distance of M to K and L, right? So for that, we will be using this formula. So if from M to K and L, let's say we want to calculate the distance of M to K. So what we'll do is we'll take the distance of M is now originated from I and J, right? So we will take I and j, the distances of I and j, and we will estimate a distance for k. Okay. So what will be that? So of the ancestor with k. Okay. So what we will do is we will take I to k, which is 21, plus j to k, which is 12, minus I to j, which is 13. Okay, we'll do this divided by 2. So this will be equal to 20 by 2, which is equal to 10. So that will be the distance of this ancestor to k, which is 10. Okay. Similarly, to L, we will calculate. I'll calculate once again from M to L, which is ij to L. So I to L we will take, which is 22. Okay. Plus j to L, which is 13, minus I to j, which is 13. Okay, this will be divided by 2, which is equal to 22 by 2 equals to 11. And that will be the distance of M to L. Okay, so this one we will calculate for the remaining set of spaces, which is basically we have compressed this ij into an ancestor. So this ancestor spaces with the other spaces. We'll calculate this d. Now we calculate d star. So for now to calculate d star, notice that we no longer have four spaces. We are having three spaces. So 3 minus 2 and will now be equal to 3. Okay. So now again we have to calculate this total distance for each of these three species. We have to calculate, we will take n is equal to 3. So 3 minus 2 equals to 1. So this value will become 1 for this particular D star computation. And then we use this formula and this total distances will be these new total distances, not this one. Okay. We will be using this set of total distances to calculate this D star for this particular set of species. Okay. So we calculate D star again. Like let me take one example for M to K. Okay, M to K, N is equal to 3. So N minus 2 is 1. 3 minus 2, which is equal to 1 times dxy. So dxy, d is M to K. Okay, so M to K is 10. So 10 minus total distance for M, which is 0 plus 10 plus 11 equals to 21. Okay, minus total distance for k, which is 10 plus 0 plus 13 is 23. This is the d star value. So this will give us minus, this is 4 minus 34. So we are getting minus 34. Again, we repeat the same thing. Here we are having, we want to find the minimum value. It may be possible to take M to K or M to L. All of these values are the minimum value. So I can take M to K, I can take M to L, I can take K to L. But in this particular case, they have taken K to L and they have repeated the same procedure. They removed this K to L and K and L rows, and now M to M will be constant. K to L, they have renamed their ancestor for K to L. So we have K, we have L, and they have renamed this ancestor as A. Okay. Now we want to compute the distance of M and A. So we will use this particular distance matrix to compute the distance of between M and A. So how do we compute the distance between M and A? So we take the distance of K to M, which is 10. We take the distance of L to M, which is L to M, which is 11. Okay, minus the distance between K to L, which is 13, divided by 2. Okay, so this will be equal to 21 minus 13 is 8 by 2, which is equal to 4. Okay, so now coming to the construction of the tree. So we know we have we have these two spaces called M and A, and the distance between M and A is equal to 4. So we add the distance between them as 4. Okay, so then what we do? We are going to split this A into K and L. We had merged K and L into A, so we are going to split A into K and L, and now we want to compute the distance to this and this, right? So we know the distance between K and M was equal to 10. So this length is 4. So this definitely has to be 6. Because this plus this was equal to 10. K and M, distance between K and M was 10. So that is why K to M will be equal to 10. But K to M to A was 4. That means K to A has to be 6. Similarly, we take L to M distance. L to M distance is 11. But M to A is 4. So that's why L to A will be equal to 7. Okay. And then again, we go back one step again. Here we had merged ing to form M. So we are going to split M again into ing, and we will use this distance matrix to notice that I to K was equal to, distance between I to K is equal to 21. But here to here, K to M was equal to 10. Okay, we know that this length is 10. So this length has to be 11. Okay. We don't really need to use just I to K. I can use I to L also. Okay. Similarly, J to I, we know that it was 13. We know that this length is 11, so this length has to be 2. Or I can use J to K also. J to K was equal to 12, but this length was 10, so that means this length will be equal to 2. Okay. So this is a brief summary of what the neighbor joining algorithm is. Okay. Now coming to ultrametric evolutionary trace, this is how ultrametric.
Ma'am,
Yes. Hello.
ma'am,
You're not audible. You're not audible.
we are going to the next
Hello?
level.
Hello?
Go.
Sorry, you're not audible.
Tell us in which.
Tell us in which?
Can you hear? Hello, can you hear me?
Yeah, now it's clear. Hello? Hello?
Hello, ma'am. Yeah, his voice was breaking.
Yes,
Am
his
I
voice
audible
is
now?
breaking.
Am I audible now?
Your
Yes.
voice is still breaking.
Okay. Am I audible now?
No, it's breaking. Breaking. It's breaking. Can you
Okay.
put it in the chat box? Can you put your question in the chat box?
Okay, no problem. Yes, yes.
Hello? Let me go to the chat box. Hello?
Yes, ma'am, you are audible.
Okay, his question. Yeah. Can you tell when to use which algorithm? Okay, so see, if you know that the additive algorithm is, if the distance matrix is additive matrix, then it will definitely generate a tree, so you can use additive phylogeny algorithm. But if you want to use neighbor joining algorithm also, it is well and good. Neighbor joining algorithm will give you a tree definitely, no matter what, even if it is not an additive distance matrix. So if you are not sure whether it is an additive distance matrix or not, then you can use neighbor joining algorithm. But more specifically, coming to this kind of problems, it's very rare to face this kind of problems in real life scenarios. So it is mostly dependent on the question what is asked to you. Okay, so uh, what we usually face in real life scenario is mostly the parsimony problems. We'll look into that a little bit later. The distance matrices based problems, they do arise in several scenarios, but under those scenarios, you usually will be able to know what kind of an algorithm you will use because you may not be knowing that the distance matrix is additive. If you know that the distance matrix is additive, both a neighbor joining algorithm and the additive phylogeny algorithm will give you the same simple tree. But it may be the scenario that there are multiple simple trees for one particular additive distance matrix. In that case, the algorithms may give you different results, but it will be the correct ones. Okay, so both of the algorithm will give you the correct results. But under certain scenarios, when the distance matrix is not additive, additive phylogeny algorithm will not give you a tree. It will just break because we'll not be able to know where to add this j value here, right? Where which branch to break. Additive phylogeny may or may not give you a tree, but under that scenario, neighbor joining algorithm will definitely give you a tree. Okay, is that clear? Does that clarify your question, Leonard?
Yes, thank you. Thank you so much.
Okay, so now coming to ultrametric evolutionary trees, this is how an ultrametric evolutionary tree looks like. All of these species are in the leaves and they are currently present. So it will be all of them are at the same level. Okay, now as you go higher to the tree, this represents the age in some years, maybe million years or billion years. Okay, so this means that 2 billion years ago or 2 million years ago, this particular ancestor split into chimpanzee and bonobo, which are still available, still present. Okay, and then you go up little back into 6 million years back, where 6 million years ago this ancestor had split into something, and that one thing evolved slowly to form human beings, and the other thing slowly evolved into forming something which split into chimpanzee and bonobo. Okay, so this is what an ultrametric evolutionary tree looks like. These values are called as the age of the nodes. Okay, all of these are at the level 0, which is basically the current scenario. And as we go up, we go back in time. Okay. So this 6 means 6 is the age of this particular species or the age of this particular node, which shows that around 6 million years or 6 billion years or whatever this particular this length is, whatever the scaling factor is, around that years ago, this ancestor was present and then split. Okay, so that is how we read an ultrametric this is an ultrametric evolutionary tree. So given a distance matrix, the problem is to construct an ultrametric evolutionary tree. So we'll look into this. Let's say this is the distance matrix. So what we are going to do is we'll take the minimum value in this distance matrix. Here in this particular scenario, this is the minimum value between K and L. Okay. So K to L, this value was different. So we'll merge K and L. Again, it is very similar to this neighbor joining where we are merging these species. Okay. So K and L, we are having the minimum value of 2. So we'll merge K and L to form one particular ancestor. Let's say this is K comma L ancestor. Okay. KL ancestor. So what this KL ancestor will be now, what will be the distance to this other species? We'll calculate that little bit longer, a little bit ago. Now what will be the age of this ancestor? At what point it should be present? So notice that K to L distance will be equal to 2. So we have a distance of this plus this will be equal to 2. So in ultrametric evolutionary algorithm, what we are going to do is we'll just split this 2 into 2 equal halves, which is equal to, which will give me 1 and 1, and I'll just put that 1 over here. So this to this distance will be 1 and this to this distance will be 1 because my distance between K and L was equal to 2. So I am just going to split into half and I'll assign the length for each of these species as a half of that, which is equal to 1. Okay, so now this is my K and L. Okay, so now what I'll do is I'll just remove K and L from this distance matrix and I'll put in KL, the ancestor KL. Okay, and so now notice that I to J, this part is common. So here it will be common and I have to calculate KL to I and KL to J, right? This distances. So what I'll do is I'll just take the average of the two. Okay, K to L, K to I, which is 4, K to I, which is 4, L to I is equal to 3. Okay, 7 by 2. 4 plus 3 is 7 by 2. Okay, which is equal to 3.5. So the distance of KL to I will be now equal to 3.5. Similarly, KL to J. So K to J was 4. K to J to K is 4. Okay, plus J to L is equal to 5 by 2, which is equal to 9 by 2 is equal to 4.5. Okay, so now the distance of J to the ancestor of K and L will be equal to 4.5. Okay, this is how we compute the new distance matrix. And then we compute, again we redo the same procedure and we find the minimum value in this distance matrix, which is equal to 3 in this case. And that distance is between I and J. So we will merge I and J into one particular node. And now notice that if we divide this 3 by 2, we'll get 1.5. So now this particular distance of this ancestor will from this two will be equal to 1.5 each. So this particular node was at a distance of 1. This node was at a distance was at the age of 1.5. So in million years, if we are taking the scaling factor of million, the the ancestor between K to L was at 1 million years ago, and the ancestor between I to J was at 1.5 million years ago. Okay, then we again repeat the same thing. We'll merge I to J into one particular node, its ancestor, which is called as IJ here. And IJ to I to J will be same, IJ to KL, KL to KL is same, and KL, IJ to KL we don't know. So we will perform this computation, IJ to KL. So what we'll do is I to KL is equal to 3.5. Again the average of the same, J to KL is equal to 4.5 and by 2, which is equal to, this will be 8 by 2, which is equal to 4. So Ij to Kl will be equal to 4. Okay, so this means that the ancestor of Ij to Kl, we will just divide this by 2, which is giving me 2. This means that the ancestor of Ij to Kl will be at an age of 2. Okay, so we had this is 1.5, so I'll take 1.5 again upwards, and now this total distance of this will be the age at this point will be equal to 2. This was 1, this was 1.5, and here the age was equal to 2. So now this to this to this to this, This is the ancestor of these two ancestors, and this ancestor was at an age of 2. Okay, which is basically the distance between ij to kl. We noticed that. Okay, so now the new distance between from here to here will be 0.5, and from here to here is equal to 1. Okay, so the new distance between ij to kl is equal to 1.5, and this is called as the ultrametric distance. Okay, so remember, whatever will be the distance in this distance matrix, you divide by 2, and whatever you get will be the age of this node in the tree. And so now if you compute the distance, this distance will change. So this distance is called as the ultrametric distance. Okay, because it is the distance in the ultrametric tree. That is why it is called as the ultrametric distance. It may be possible that ultimately once you construct the ultimate ultrametric tree and then you calculate the distances between these pieces, the ultrametric distance and the actual distance matrix, these distances may differ. Okay, so this is how we compute the ultrametric tree, and the ultrametric distance. If you compute here, I to j is same, which is 3, but here if you notice I to k, it will become 2 plus 2 is equal to 4. So I to k is equal to 4. In case of, if this is an additive distance tree, if additive distance matrix, then the ultrametric distance and the additive distance will be same. But in case it is not, then you will get an ultrametric tree, and the and then the distances will be different. So in that scenario, these distances will be called, the new distance matrix will be called as the ultrametric distance. Okay, so that is about ultrametric evolutionary tree algorithm. And then coming to the small parsimony problem. So what the small parsimony problem is, we are given a binary tree, which is basically you will be given the evolutionary tree, and you want to label these
Uh,
nodes. Okay.
Ma'am, am I audible
Yes.
now? Am I audible now? But
Yes.
still it is breaking.
Yes.
Okay, so ma'am,
No, it's
during
not.
the, is it audible now?
Yes.
Hello. Okay, ma'am, during the lecture it was,
Yes.
hello, am I audible?
Yeah, during the lecture. Hello. Hello. Okay, Lalit, please post your question on the chat box and we'll clarify a little bit later. Okay. I'll just complete this parsimony problem. You keep posting your questions on the chat box and I'll clarify them at a time. Okay. Hope that is fine. Will that be fine, Lalit? Am
Yeah,
I
he
on?
is writing. Yes.
Yeah, okay. I'll just go to small parsimony problem. Okay. So in the small parsimony problem, what we do is we are given this rooted binary tree. Okay, and each node we will be labeling with a string. Okay, so we have this ACGT. We want to know how many occurrences of C are there, how many occurrences of G, and so on. Okay, so we want to label these nodes in a way that we will get the most parsimonious labeling. That means that Hamming distance, the distance between these pieces, will be uh, least. Okay, in other words, we want to guess what these pieces are. Interestingly, we already know these species, right? We know what these current species are, but we don't know the ancestors. So given this tree, we want to use these known species to find the ancestors. Okay, so this is the small parsimony problem. Here what we do is, see, here we suppose we have this label of C, and we have a label of C, which means that the distance from this to this. Okay, if we have a C here, if we have a C here, then the distance, and if we have a C here, then the distance will be 0. So that is what we have here. This value for C at this, if there is a C here, then the distance value will be 0. Similarly, if we have A here, then the distance will be A to C and A to C, which will be equal to 1 plus 1. So it will be equal to 2. If we have a G here, G to C will be equal to 1, and G to C, the distance will be equal to 1. So the total distance between the two species will be equal to 2. And for T, we again have the same thing. So if T to C will be 1 and T to C will be equal to 1, so T will have the value 2. Okay. Similarly, let's say for this particular node, we have A here and C here. So A, if we put the A here, the distance will be 1. If we put a C here, the distance will be 1, but if we put G and T, the distances will be 2 and 2. So now coming to this particular position, if we have a value of A here, how do we guess here? For here we can only put A, C or G or T. Okay. So if we are putting A here, what will happen? If we put A here, the distance to this, if we have A and A, the distance will be 0, right? But if we have the A here, A to A will be equal to 2, A to 1, here we have A to 1, okay, so this will be 1, and here the minimum of this value is 0, the minimum of this value is 1, so let's say, so for A to, if we put a C, so because the minimum value is 0 here, we will be having the C here, because the minimum value is 1 here, we can have an A or C here, okay, so if we put an A here, the distance will be A to C will be equal to 1, and here we can either have an A or C, so the distance here will be 1. Okay, so for A it will become 2. Okay, but if we put a C here, then again the same scenario, we will have C to C will be equal to 0, but here we will be having an A or a C, so that's why we will be having a distance of 1. The maximum distance possible will be equal to 1. Okay, and so on, we use a DP algorithm to calculate what are the symbols that we can be putting over in this particular locations. Okay, this is pertaining to just one particular position of the DNA sequences. We have this long sequence for this particular species, a long sequence for this species. For every one of those positions, we can compute the small parsimony score. This is what the small parsimony problem is. Okay, the large parsimony problem is the reverse of that. We are given this set of strings and we want to find this particular tree. Okay, we just have the strings. We don't have the distance matrix. Using the distance matrix, we can compute those. You can use this distance matrices to compute those trees and everything. But here, using these strings, can we find the tree? Okay, and this particular problem is anti-complete. So these two problems are actually character based because we are considering ACGT instead of the distances between these species. Okay. So the reason why the distance based methods are not that not that taken into consideration, and people are working on this large parsimony problem even though it is anti-complete, it's because of the fact that they are distance based matrices. We are just taking the Hamming distance. We don't really know whether the Hamming distance should be the correct way, or is it the more like of a norm to method, L2 norm, or whether it's an infinity norm. We don't know exactly how to compute these distances. Given this distance, we compute the tree, then we can go to this distance based methods. But we, in practice, in real life, we don't really know whether how relevant this distance based methods are, how this distance matrix will be computed, how this distance like whether how significant this distance-based methods are. Using this distance-based method to construct an evolutionary tree, whether how significant that is not yet known. How to compute that, how to measure this distance, that is also a question mark. So that is why people are more working on this large parsimony problem, where we use this DNA strings to compute the evolutionary tree. Okay, so but the question is, large parsimony problem is an anti-complete problem. That's a brief summary of this week's content. Okay, so actually there are a lot of content, lot of work on this evolutionary trees. So there's an entire segment. There are books on this, only on this parsimony phylogeny construction problem. There are entire parts of books on this phylogeny construction problem. So there are a lot of works on this in this particular field. So you can read more for that. Okay. Okay. So let me just go to the doubts. Yeah. Leave it, my net is back. If it is an additive matrix, neighbor joining algorithm, you can also use a neighbor joining algorithm. If you know that the matrix is an additive matrix, then you can use both an additive algorithm or a neighbor joining algorithm. Both of them will give you the same correct tree. Okay, there is no constraint in that. If it is a non-additive matrix, then you have to use Neighbor joining, that is true. That is for sure. Additive algorithm will not give you a tree if it is a non-additive matrix. But if it is an additive matrix, then you can use either of the two algorithms. There is no constraint. Both of the algorithm will give you the correct tree. Okay. Okay. Any other questions?
No, ma'am.
Okay. In that case, I'll stop the streaming and we'll close the session. Okay then. Thanks.
Thank you, ma'am.
Thank you.